So now we begin Chapter 13. Chapter 13 deals with acids and bases. And this chapter is by far one of the most important that we cover in this entire course. And not just for this course, but these ideas of acids and bases are things that you're going to see over and over again in any chemistry courses or anything related to chemistry that you might do in the future. If you take organic chemistry, you'll certainly see these concepts again, and you'll definitely see them if you take biochemistry. So we start out by talking about a definition of what acids and bases are. And that might seem like it's a very, very simple, straightforward question to answer. The problem is, there's actually multiple definitions of what acids and bases are. We're going to cover 3 of them in this class, but there's actually even more than that. So we'll start with the Arrhenius definition, which dates back to 1887. And while it's the least useful of the 3 we're going to cover, and the oldest of the 3 we're going to cover, it's still important. After that, we'll talk about the one that we use probably more than any other, which is the Bronsted-Lowry definition. That dates to about 1923. And finally, we'll talk about the Lewis definition, which dates to about 1930 and is by far the most comprehensive. So the Arrhenius definition is that an acid is a substance that produces H+ ions in water. And a base is a substance that produces hydroxide ions in water. Now, we will also talk about what a strong acid versus a weak acid is. And so the Arrhenius definition defines a strong acid or a strong base, but if we use the term strong, it refers to one that completely dissociates. Now, what are the problems with this definition? Because there's a couple fundamental problems with this definition. So the first fundamental problem we find here. It assumes that everything we're dealing with is within water. And while in a class like this, everything we do takes place in water, in chemistry, not everything takes place in water, and sometimes we have to deal with other solvents. So that's a very limiting factor. The second thing is when we say it produces OH ions. Are there bases that don't produce OH ions? The answer is yes. And so those 2 factors become very, very limiting on the Arrhenius definition. So going ahead a few years, Bronsted and Lowry came along, and they gave a different definition for an acid and a base. They said that an acid is a proton donor. A proton being the term that we use to refer as a hydrogen cation. Now that should make some sense because a hydrogen atom is 1 proton no neutrons, and 1 electron. So what happens if it's H+? Well, that means it's lost its electron. And so what's left is 1 proton. So that means you could always tell the following. An H+ ion walks into the bar, and the bartender says to the ion, you don't look happy. What's wrong?" And the ion says, "I've lost an electron." And the bartender says, "Are you sure?" And the ion says, "I'm positive." So if an acid is a proton donor, then a base is defined as a proton acceptor. Now, for almost all acids and bases, this definition works very, very well. And so acids and bases often undergo reactions called neutralization reactions, where an acid can react with a base to form water and a salt of some sort. The problem became that they eventually found there were some compounds that behaved very much like acids and bases, but didn't actually give up protons. And so that brings us to the Lewis definition, which, as I said, is the most comprehensive and the most complete definition. And the Lewis definition focuses on electrons. That should make sense when you think about it, because we know that if we're donating a proton or accepting a proton, then we have bonds forming or bonds breaking. And we know that bonding is controlled by the electrons. So it makes sense that we would want an acid-base definition that focuses on what the electrons are doing. So finally, Lewis defined an acid as a compound that accepts a pair of electrons, and a base is a compound that donates a pair of electrons. Now, we also have compounds that fall into a category known as amphoteric compounds. These are compounds that have acidic and basic properties. In other words, under the right setting, they can be an acid, but under a completely different reaction environment, they can function as bases. Best example of this is water. So if you add an acid to water, it can pick up that proton and form H3O+. So here, water is functioning as a base. But you could also add water to hydroxide, and that will remove a proton from water. In that case, the water functioned as an acid. Now, for every acid-base reaction, we can talk about what are known as conjugate acid-base pairs. So what this means is we have an acid which is going to react with a base. Now the acid after it gives up its proton, it's now going to turn into something that can function as a base. So we call that the conjugate base. Whereas the base gains a proton and it can function as an acid. And we call that the conjugate acid. So let's look at an example with some actual compounds. So water plus HCl reacts to form H3O plus Cl minus. Now we draw all of these reactions now with equilibrium arrows because they are in theory reversible. And we'll learn later on how we can predict which side of the equilibrium an acid-base reaction will go to. But here we know that the HCl is giving up a proton. We know that because it becomes Cl minus. So in order to become Cl minus, it had to give up a hydrogen. So the HCl is the acid. What's the Cl minus? Well, the Cl minus no longer has any protons, so it can't give any away. So it's something that could function like a base, or we call it the conjugate base of hydrochloric acid. Water here was our base, and we can see it's the base because in the product it has added a proton. By adding a proton, it now has an extra proton and becomes a species that could give up a proton, so we call it the conjugate acid. And so this is something we will see for every acid-base reaction, is that the base picks up a proton, it forms a conjugate acid. The acid gives up a proton, forms a conjugate base. And that's what makes these processes reversible. Now, one of the interesting things we find is that there's a relationship between the strength of a base and its conjugate acid, or an acid and its conjugate base. So if we have a strong acid, what does being a strong acid actually mean? Well, earlier we said that a strong acid is one that completely dissociates in water. And then we talked about some of the limitations of that definition. But what we can take from that is that a strong acid is an acid that very, very easily gives up a proton. And the stronger the acid is, the more easily it gives up the proton. So after a strong acid loses a proton, it's going to form a conjugate base. Is that conjugate base that forms going to be weak or strong? Well, if that strong acid is very willing to give that proton away, does it want the proton back? The answer most likely here is no. And so a strong acid, after it loses a proton, gives a weak conjugate base. What if we have a weak acid? Well, a weak acid will give up a proton, but if it's a weak acid, it doesn't want to give that proton away. And so does it want the proton back? Yes, it does. So a weak acid will give a strong conjugate base. And the same sort of logic is true for the strength of bases. So what if we have a strong base? Well, a strong base is one that's going to want to gain a proton. So if it's going to want to gain a proton, does it want to give that proton away? Most likely no. So a strong base forms a weak conjugate acid. And finally, as you would logically expect, a weak base doesn't really want to add a proton, and so it's very happy to give it back. So in general, in terms of trying to recognize acids and bases, an acid has to be either positive or neutral, and is often a hydrogen bonded to a highly electronegative element. Whereas a base is going to be something that needs to have a lone pair of electrons to give up, and will have a negative or a neutral charge. So we've talked sort of qualitatively about what it means to be a strong acid or strong base. But is that something we can actually define numerically?